Steady state error. Let's define something called static error. We looked at this last time. E-step. Steady state error for a step input is given by one over one plus seven and distance is equal to G. And steady state error for ramp input is defined as 1 over limit of here. We introduced three steady state or static error constants called position error constant, velocity error constant, and acceleration error constant. So Kp is defined as limit and this tends to 0, 0 plus Kb is limit and this tends to 0 when 0. So in terms of the static error constants, the static error constants here are Kp is position error constant. Kb is so in terms of these static error constants, you can redefine or you can re-express the steady state error as 1 over 1 plus Kp. And we relate, so there is a relationship between steady state error and system time. So what is this system time? there are three types. Type 0, which means there is no pure integrator. One pure integrator. And type 2 So we looked at this, right? For type 0 system, what is this? It is, last class, do you remember? For type 0 system, this is finite. This is infinity. This is infinity. Okay? For type 1 system, 0, finite, and this is infinity. In type 2 system, this is 0, 0, this is finite. So this is, with respect to the exam or an assignment, this is how you should approach it. Okay. So if you're given a, let's look at an example. So the following system find the steady state error. Or let's make it a little more, another step, we introduce another level of complexity. We given this system. So you give something like this and you may ask to find the value of k. If the steady state error is 10%. Okay. So what type of system is this? First you have to identify type of system. What type of system is it?
Type 1.
Type 1. Okay, it's a type 1 system, right? There's only one pure integrated. So obviously, what is the you're going to use E RAM, correct? You cannot use anything else. You cannot use this because this is 0. This is finite, and this is, it's a type 2, type 1 system because there is one pure integrator. So you cannot use these two. You have to use this, right? ERAM is this. Okay. So what do you need for ERAM? You need KB. For type 1 system. KB is what? Limit
S.
as s tends to 0, s into
J.
G of x. So this is complete. K into 5 over
6.
6 into 7 into 8. So this is 5 3 over 56 into 6 is 300. 6 is 336, right? KB is 5K. Now, second step is you need to figure out E rank. E rank is what? How much is this?
Put the S, the J, S, and S cancels out.
E ramp is given to be 10% or 0.1. Hmm?
Then it's because it's over
Right. So this would be equal to 1 over 5K into number. You see it? We have this, therefore K would be 33, 3360 over 5, it is 5, 6, 7,
So what's it like? 1 over 5K over 336 is 0.1.
that's what is given, right?
It's given. Oh, okay.
What is given is if the steady state error is 10%. And that is what we are equating to. So E ramp is, by definition, E ramp is this, right? The trick here is that you immediately identify that this is a type 1 system. So only one of this is going to be, you'll have to use just one of these. And you don't really have to memorize this, okay? If you want, you can memorize, but it's fairly simple. It's fairly intuitive. Everything starts with the definition of steady state error. If you know what steady state error means, you can arrive at, for example, if we were to solve this by first principles, okay? So this is How do you define steady state error? E infinity what is steady state error in terms of G of S? Do you remember? Do you recall? Hmm? Regardless of what kind of input. You can even go.
The limit,
Huh?
the limit is S versus 0 of S times R of S or times inverse.
So this is limit of S tends to 0, S
S times R of S over 1 plus G of S.
1 plus G. You can go a step behind this as well by looking at what is error signal. Error signal is C of R of S minus C of S, and then you just have to express C of S in terms of G of S, and then equate. You set the limit of S equal to 0. Of course, when you are doing this, you will be allowed a cheat sheet, so you can at least note down this formula. Okay? So this is your basic definition of steady state error. What is this for a step input? We have limit.
That's
So it would be 1 over.
Huh?
It would be 1 over 1 plus over.
With S equal to 0, 1 over 1 plus, we have K pi, this would be 1 over S into S, right? This cancels. We have K pi S into 6 into 7 into 8. Okay, or 0. Right? All you're doing is substituting S equal to 0. So you see this, immediately it should strike to you that this is 0, because this term is infinity, right? It's something over 0, which is infinity. So 1 plus infinity is infinity, and 1 over infinity is 0. So this will, you rule out this, saying, okay, step input does not work. Now let's see ramp input. Okay? So what is ramp input? You have S 0, S into 1 over S square, right? Then you have 1 plus 5k over S into 6 into 7 into 8. Okay? This S cancels with this, so if S comes to the denominator, and you have limit S tends to 0, 1 over S plus 5sk over S into 6 into 7 into 8. So you have S, this goes to 0. Right? So you see, this is given to be 0.1. 0.1 is equal to 1 over, or this is 336 over, again this results in k equal to.
So what you did initially before you erased it was what again? What you did initially before you erased it was what? What was the point of that?
Step input. We did the first thing for step input.
No. Here, when you said
Yeah,
it would
we
work.
did the step input.
So this is rapid input? Okay. Wait, so why don't we try step input when we could listen? I don't know.
Did you attend the last class? Okay. I'm just trying to understand, because see, this This is what we discussed in last class. The entire context of last class was this. There's something missing because everybody else is everybody else clear, or am I doing something wrong? Did you understand the point what I tried to make here? Right? We have come to this point starting from first principles, right? We defined steady state error, and we defined steady state error with respect to limit, right? When limit s tends to 0. And then we define steady state error for 3 specific inputs: step, ramp, parabola. And then we define type, the system type. And what I'm trying to say here is, you can look at this and recognize the system type and correlate that for a particular system type, only one steady state error exists, or steady state error for only one input will exist. The other two will be either 0 or infinite. If you don't want to do that, you can start with first principles. This is the basic definition of steady state error. If you remember this, you can substitute R of S is equal to, because here you have to understand that input will not be given to you. You see the problem, the input is not given, right? So you have to know that for this means, see, these two information combined to say that the input is a ramp input. If you don't remember that, you can go by first principles and substitute R of S is equal to step, ramp, parabola. And you should arrive at, if you put a step input here, you're going to be, it ends up to be 0. So you say just eliminate that. Right. So you eliminate that and then go to the next one.
Okay, that was really my lesson. So, okay, just.
Is everybody else clear on this? Why we are discussing this?
No, now,
For where it says number 2, we got B ramp is equal to 0.1, that's the 10%, right?
That's a 10%.
Okay.
So that's 0.1, right? 10% is. It's 10 over 100. So that is what we have done. E ramp by definition is 1 over kV. We found kV, which is limit this thing. There's a value for kV in terms of kV, right? We just substituted that and we found out.
Okay, fine.
That's it. You will be allowed a cheat sheet. You will be allowed a formula sheet for this. But you need to recognize what is the problem. That's it. And that is really what you need to be as engineers. You don't really need to memorize a lot of things, because that's what books are. That's what writing down stuff, right? Making sense of it is what you need to think as engineers.
Dr. Sunday, would you feel like if you had to get a master's in systems engineering, would you want to do it online?
See, if you are doing any kind of master's, what is the motivation for doing a master's? If it's just a matter of getting extra money, then why not?
Yeah.
Right? But if it means that you want to learn something, see, you understand now. You should understand the environment, right? School environment, and you're going to be in the corporate environment for what? The rest of your life. It's not such a big harm to come back to school and enjoy another 2 years.
So basically, you would be online programs.
I'm not against it. I'm just saying, if you are, let's say, you get married, you have a family, and that's understandable, right? That time you want to do it online. You don't want to go to school. But when you have the opportunity to go to school, why not?
An opportunity present itself. This free master's program they're talking about offering is systems engineering here.
Here?
What?
It's saying, well, I mean, if you're an alumni, you're supposed to be able to get a master's here for free.
That was something they told us to do.
Frankly, I would say go to a better school.
I feel that.
I'm not saying this is a bad school. No. Whatever undergraduate degree you get from a particular school, you should strive to get a master's degree from a better school.
From a better school.
We don't
Okay.
have masters degrees.
Absolutely.
Huh?
We don't have facilities.
That's why the online thing is real tempting. I was like, well, I can do it at my house. Yeah, then I can be working and get a master's. That's all I'm doing.
Do it if it's just a matter of getting a degree, then you do it. But if you want to educate yourself or want to learn,
Yeah. It's something to think about. Yeah. Free. That was free. So like, ooh.
I mean, you get to like some company, most of the days, you work with them for years, so.
Yeah, true.
They'll pay for you.
This is the only thing that I was weighing on. Like, well, if I do it, I can start small. And be working. Yeah, and be working. You know. Definitely get a doctorate. I'm gonna do
alright,
that.
let's take a look at one more example.
Because by then,
It says method from first principle. We'll discuss a little bit about steady state error. For non-unity feedback system. So you have to understand, when we started this discussion, everything was defined for whatever we defined it for a unity feedback system. It should be very obvious to you that there are very few systems which are going to be unity feedback systems, right? So what is a unity feedback system? You have to think about a non-unity feedback system and a unity feedback system. Let's discuss a little bit about non-unity feedback systems. Okay? When you sense the output, if you can directly feel the output and affect the input. For example, if you're controlling the temperature, right? You cannot really directly sense the temperature and feed that into a system which will adjust the temperature flow, right? So this is not really temperature flow, right? You cannot really have a temperature input. You can have heat input, but most often than not, what are you going to have? You're going to have an electrical input, right? You're going to vary the voltage more often than not. So what you need here is something which will transduce that heat or that temperature into, senses that temperature, and then converts that to voltage. And then you can see the difference in the voltage. The input voltage is, if the input voltage and this one is the same, this is going to be 0, right? The error is going to be 0, and the system is going to get switched on, right? So you can think about, you cannot really think about a system where you have a unity feedback system, where the output will not be transduced or not be transformed. It will always, more often than not, it will always be transduced. There are only, when you're dealing with electromechanical systems, there are only three things you can sense, really. So what are the three things? You have voltage, you have current, and what is the other? Huh? You cannot really sense temperature. You can really sense the frequency or the time factor. Okay? So these are the three things, these are the only three things which actually can be sensed. And everything else is just a converted. For example, if you think about sensing distance. How do you sense distance? It is frequency. It is a time of flight. For example, if you're thinking about ultrasonic this thing, you have a ultrasonic sensor. You have a transmitter and a receiver. Okay, so it's going to transmit something, and the time is noted down when that signal is transmitted. Okay, and then this thing is going to receive that, and based on the velocity of sound, right? So based on the distance, you can figure out how far that particular object is. That is also the case for infrared sensors. If you time it right, infrared sensors will give you a time of flight. So the time of flight from transmit to receive, and that is how you sense your distances. So similarly, you can sense current or voltage, and color is again sensed as current or voltage. You have color sensors. You have line followers, you have all these different types of sensors. Camera again is a current or a voltage sensor. Okay. If you have something like a non-unity feedback system,
They wouldn't let me get it because I didn't have a sticker. And I was like, excuse me,
Bro, I'd be so mad.
A sticker?
Right here.
yeah.
see, whenever you have something like this, this is your error signal here, right? So you have G of S. This is H of S. So you can define your error signal as, here it is, R of S minus H of S into C of S. Right? And then, but what is C of S? C of S is simply E of S into G of S. Okay. Once you have this, so your E of S now is what? One plus GS H is equal to R. Therefore, E of S is equal to R of S over 1 plus. Okay. you have this, all you need to do is you have to define E infinity is limit as s tends to 0, s r of s over 1 plus g. And you just simply apply the so if you simply apply this definition, E infinity would be what? Limit as s tends to 0. You have s 1 over s. You have 1 plus GS HS. So you have GS, you have 100 over 0. Again, this is not going to work because you're going to end up with a 0. So if you're going to do step it, this is for step. So this is not going to work. What is it for ramp? S tends to 0. S into 1 over square over 1 plus 100 over s 10 1 over 5. Now this will be limit s tends to 0. You have s, s. You have 100 over 10 right?
This one over. You put that line here, Dr. Sun.
Hmm?
You put that line here. One over 100 over 10. You just make it a fraction.
Like, see the
One over that.
the one in the numerator.
Mm-hmm.
Yeah. Floating.
You can simply do this, or what you can do is you can convert this to a unity feedback system. If you have not yet finished your lab, the last one, so this might be helpful to you. Okay? You have G of s. So what I'm going to do is, this is equal to equal to two signals. So this was minus, and I added plus, and minus. Okay. So by adding a plus and minus, nothing has been changed. Okay. This is a plus signal. This is a minus signal. You see it? I have not changed anything. If we do the equivalent system, you're still going to end up with the same equivalent system. Okay. So you have minus, plus, minus.
She was like, deal,
So now you have D of x and H of x minus 1. So I've combined these two now, these two signals, and left this one as it is. So if you combine these two, this one and this one, it would be h of s minus 1, because you see, this is h of s, the minus is as it is. Minus 1 into minus 1 is plus 1. Right? You see it?
Was that it?
You follow this step? Did you follow this step? So for the next one is, we're going to combine these two. Okay? So you have h of s, this is plus 1, right? So h of s minus 1, this would be minus into minus, it would be plus 1. And h of s is just as it is.
Is that minus?
Huh?
Is that minus?
This is actually minus, yeah. This has to be minus. Now we'll just do the feedback for these two. What is the feedback? The feedback says it is g of s over 1 plus gs hs, right? So here hs is hs minus 1. That's it. Correct? And then you have minus plus. We have we'll call this GE of equivalent of then R of x minus G of E, GE of s is simply G of s over 1 plus G of s once you have this, you can again simply apply the static error constant definition for the unity feedback system. This is a unity feedback system, right? Your G of S has changed to GE of S, that's it.
Would it always become subscript E?
Huh?
Would it always become subscript E?
It's just another notation for what this is. You can use your name if you want. That's fine. So this is how you would approach non-unity feedback system.
Can you explain, okay, so, I see what you did, but what was the name for this? Did you take a non-unity feedback system?
Yes, I took a non-unity feedback system. Whatever we have learned, the steady state error definitions are for unity feedback system, right? We want to be able to apply the definitions we have learned to non-unity feedback systems as well.
Okay.
So how do we do that? We take a non-unity feedback system. We do some block diagram modification and then convert it to a unity feedback system.
Oh,
So there are I showed you two methods. One method is this was the first one. This is the second one. Okay? The first one is, again, let's go to basics. Define error. The error signal is simply R of S minus H of S into C of S. Okay? And then you define steady state error. Steady state error is what? This error as S tends to 0. That's it. Right? So you can either go by this definition or you do a block diagram reduction to unity feedback system. And this would be pretty common. You're not going to get very complex systems. Even if you get a very complex system, you should be able to convert that to a non-unity feedback system. Sorry, a unity feedback system. And get the answer. And that's where block diagram reduction becomes relevant. So that should be it for today.